In this segment, we're going to talk about the first law of thermodynamics, specifically about the first portion of that equation, which is how energy can be stored by a system. So the first law is otherwise known as the conservation of energy, and it says that the amount of energy stored by the system is equal to the net amount of energy that's transferred to the system across the system boundary. The change in energy, we refer to that as delta big E, and when you have uppercase letters, that's not on a per mass basis. So in this case, it's just units of energy, so kilojoules or BTU. And then energy could be transferred across a system boundary in different ways. It can be transferred by heat, work, and if you've got an open system where you've got mass flowing across a system boundary as well, you can have energy transferred by mass. So let's look at an example here. We've got this tank, and there's a lot of things going on, but it's a sealed system, so it's a closed system. So I'm going to get rid of that open mass notation there. And the energy E1, that's the energy associated or stored by the system at state 1. And then we have heat added to the system. We've got some work going on, work transferred. And then after all that's done, the energy stored by the system at state 2, after all that's done, is E2. So we have a delta E, which is E2 minus E1. We're going to focus on the left-hand side of the equation, the ways that energy could be stored by the system. And it could be stored by internal energy, kinetic energy, and potential energy. So we're going to focus on internal energy right now. Internal energy, if we write it as a capital U, that's in kilojoules or BTU, and this lumps together several types of energy. So sensible energy is associated with the disorganized microscopic kinetic energy, and that's different from macroscopic kinetic energy, which we'll talk about in just a second. So this takes into consideration how fast those molecules are moving around. And so in a hot liquid, for example, those molecules are going to be moving around a lot faster than the molecules in a cold liquid. So that's shown here when somebody injects a dye into a hot liquid. You can see the red dye is being dispersed a lot faster than the blue dye in the cold liquid. And that's just because those molecules in the hot liquid are moving faster. Latent energy is associated with phase change. So it takes a certain amount of energy, say if you're looking from D to E, so the phase change from a liquid to a gas, it takes a certain amount of energy to cause that phase change from a liquid to a gas. So latent energy associated with phase change. Chemical energy is associated with the breaking and forming of atomic bonds. So those first two circles are showing bonds being broken, and that would be the case if you're putting energy into the system, and that energy being put into the system is represented by the blue arrow. The last two circles are indicating that energy is being removed from the system, and the molecules are reforming those bonds. So if you've got a chemical reaction, you have a change in chemical energy and thus a change in internal energy. And nuclear energy is associated with nuclear bonds. Now, we're not going to worry so much about the individual types of internal energy. We're going to lump it all together just as internal energy and make it simple on ourselves for now. And we are primarily concerned not with the number of U, but we're primarily concerned with the change in internal energy. So delta U, delta big U, is U2 minus U1, what it is after minus what it is before, and that would be in terms of kilojoules per kilogram. That's an extensive property, absolutely dependent on the size of the mass of the system. We could put that in terms of delta little u, so that's a lowercase u with a little tail there. And delta little u is expressed on a per mass basis, so kilojoules per kilogram or BTU per pound mass. And this is an intensive property, and this is something that you can look up. So you may have noticed that you've got columns for little u in your tables, and specifically in your saturated tables, if you're saturated, you've got a value for U sub F and U sub Fg, or U sub F and U sub G, and you can calculate what the internal energy is of a two-phase substance in the same manner that we did for specific volume using quality. And some tables have a column for U sub Fg. This table doesn't, but some tables do, so just be aware of that. It's just U sub G minus U sub F. They were nice and did the math for you. Now let's look at kinetic energy. So kinetic energy, big KE, is in terms of kilojoules or BTU. And we're primarily concerned with changes in kinetic energy. So delta kinetic energy is what it is after minus what it is before. And this is 1/2 times the mass of the system times v squared at state 2 minus v squared at state 1. And you'll notice that there's a little vector notation over here. That's just to indicate that it's velocity. So I'm not going to be worried about the direction. It's just a magnitude. But I do want to, I put the little vector notation or the little arrow over it just to differentiate it from volume. So this is an extensive property, but we could put it in terms of little kinetic energy. So lowercase kinetic energy, which is expressed on a per mass basis. So you'll see the only difference between the top and the bottom equation is there's a mass term left out of the bottom equation, and that's just because you divided it out. This is an intensive property. It's not something that you're going to look up. It's something that you calculate. And the way that we think about kinetic energy changes in an open system versus a closed system are going to be different. So let's look at it in a closed system. So here I've got a box and I've got a liquid or a gas or something in this box, and I'm interested in analyzing it. And you can see that the molecules are moving around, but they're moving around. They're moving around with a kinetic energy that's microscopic kinetic energy. So let's say this box here, this tank that contains this liquid, is stationary. So the initial state of my system is 0 because the system as a whole is not moving. Maybe the molecules are moving around because they have sensible energy, but the whole tank itself, the system itself, is not moving. And so the macroscopic kinetic energy is 0. Now, if I take that same box, and I'm interested in that box, I'm interested in the kinetic energy of that box. If I take that same box and I put it on a truck and it starts moving with a certain velocity, well, now it does have kinetic energy that's greater than 0. So your kinetic energy change would be the kinetic energy at state 2 minus kinetic energy at state 1, and it would be a positive number. Okay. Now, a word of caution, let's say that we've got that same system, but we put a paddle wheel in there. So the paddle wheel turns and it spins the fluid in there. And right now it's off. So it's initially off, and that whole system is just sitting there. It's stationary. So the velocity is 0 and the kinetic energy of the system is 0. But now I turn the paddle wheel on. And so the paddle wheel starts to move and the molecules in there start to move with a greater microscopic velocity. What would be my kinetic energy? What would be the kinetic energy, the macroscopic kinetic energy of the system as a whole now? Well, it turns out the kinetic energy would still be 0 because the whole system is not moving. So just be aware of that. Sometimes people get a little bit confused about that. What that manifests itself as, because we do have an increase in microscopic kinetic energy, and that would manifest itself as an increase in internal energy, little u or big U. All right, so now let's look at the change in kinetic energy in an open system. So you're probably familiar with garden hose nozzle, right? So here we've got a nozzle. We'll talk about nozzles quite a bit as we go on in the semester, but what you've got is you've got fluid coming in and you've got fluid going out, and the fluid going out is going out faster than it's going in, right? And I might be interested in how that flow changes, maybe specifically how much the velocity changes from the inlet to the outlet. And so I would do a control volume analysis. I would draw a control volume around a region of space that I'm interested in analyzing. And so I would be looking at changes from that first arrow to changes to the second arrow. So the kinetic energy of the fluid crossing the boundary at that first arrow on the left would be 1/2 times little v1 squared. So that, or not little v1, but v1 squared. So the velocity at state 1 is the velocity of the fluid going in at the inlet. And then the kinetic energy at state 2 would be a lot higher than the kinetic energy at state 2 because the velocity would be higher. So it's just a different way of thinking about changes in kinetic energy in an open versus a closed system. All right. Last thing, changes in potential energy or potential energy. So energy could be stored by a system by internal energy, kinetic energy, and lastly, potential energy. So potential energy, delta potential energy, changes in potential energy with a capital PE. This is in terms of kilojoules or BTU. So it's M times G, which is the gravitational constant, times delta Z, which is the change in elevation, so Z2 minus Z1. And this is an extensive property, but just like those other properties, we could put it in terms of little potential energy, lowercase potential energy, which is on a per mass basis, kilojoules per kilogram or BTU per pound mass. This is an intensive property. It's something you calculate, it's not something you look up. And the way that we think about changes in potential energy are different for a closed versus an open system. So for a closed system, let's say you've got a box and it's got something in it and you're interested in analyzing it. And at state 1, it's sitting on the ground. And then somebody comes along and they pick it up. So your change in kinetic or change in potential energy would just be G times the gravitational or the elevation change, Z2 minus Z1. So this would be in terms of BTU per pound mass or kilojoules per kilogram. Change in potential energy in an open system. Say you've got this set up. So you've got a pump that's pumping fluid from tank 1 to tank 2. So it's pumping it up in elevation essentially. So this is a classic scenario where you might be interested in how the flow changes from the bottom to the top. So I'm drawing my control volume here, and I'm interested in how flow is changing from the inlet of this control volume to the outlet. And I have a change in elevation, a total change in elevation of 50 feet. So my potential energy change is G times delta Z. Okay, so I get things in terms of feet squared per second squared, but I keep mentioning that little potential energy, it's always in BTU per pound mass or kilojoules per kilogram. So I do need to do some unit conversion. I just look at my conversion tables and get the units to cancel out until I get things in terms of BTU per pound mass. All right, so this is another example where unit conversions are really important. Let's see, last thing, the change in energy stored by the system equals the net amount of energy transferred to the system, and the ways that energy can be stored by the system are internal energy, kinetic energy, and potential energy, and you can express this on a per mass basis, or you can express this in just as extensive properties, so delta U, delta big U, delta kinetic energy, delta potential energy. All right, well, I guess that's it. I hope you learned something, and thank you for watching.